Good afternoon, everyone. Nice to hope it's nice to hear from me. Today we're going to talk about alcohols, how to name them, identify the difference between primary, secondary, and the light's in the way. Secondary and tertiary alcohols, and we're going to talk about solubility and boiling point. So, first things first, alcohols. Alcohols are easily identified by the presence of an OH group somewhere on their chain. So, the OH group here is quite often present at the ends of chains, and you can identify that and name that using the prefix hydroxy, or the suffix ol. Now, hydroxy or ol, when to use them, it's a common problem that people have. Hydroxy is used when you're using have a longer chain molecule that has no suffix, for example aldehydes or ketones. So let's go with propanal here. So if I have propanal and there's an OH group on there somewhere, for example on carbon number 2, that would be 2-hydroxy propanal. Much more common for you guys is the use of the suffix ol, and for examples of that you have methanol, ethanol, propanol, butanol, pentanol, decanol, and so on. If you have all your OH group located in places other than the end of the chain, or in multiple places, you would use something, whatever it is, number 3 ol. So for example, this one here would have an OH group on carbon number 3. So for example, butan 3 ol, or so butan 3 ol to show that it's on carbon 3, even though that wouldn't make much sense because actually that has a stereoisomerism, so actually be butan 3 ol is the same as saying butan 2 ol. You'd have to have other substituents there for that differentiation, but that's okay, that comes with the territory really. Now, so that's naming under the way. Now we're going to talk about boiling point and solubility. So I'm going to talk first of all here about boiling point. Now, with boiling point, we're saying it's relative to alkanes. And I'm saying relative to alkanes with the same chain length. So, for example, we'll be comparing ethanol with ethane, for example. Yeah? Or propanol with propane. So, respective to their just aliphatic alkane form, the boiling point of alcohols have an increased boiling point compared to their alkanes, and this is due to hydrogen bonding between individual alcohol molecules. Now, to give you an example here, I'm going to use propanol. So propanol, I'm going to draw it skeletally here. 1, 2, 3. 1, 2, 3. And then here is our side chain here. Yeah? So on this OH here, we have, if we zoom in a little bit onto this OH here, zoom in to an O and a H here. And in fact, you could zoom in even further with more detail. Here you have an oxygen, 2 lone pairs, there's an R group there, another lone pair there, and then our H here. Now, if you remember, oxygen is very electronegative, meaning it draws in bonding electrons incredibly strongly. So that's going to form a delta negative charge, and this hydrogen is going to have a delta positive charge, and that's going to attract adjacent and nearby alcohol molecules, in fact adjacent propanol molecules towards them. So if we're going to draw in an adjacent one here, this delta positive charge here, this is going to be attracted to this lone pair of electrons here. And that's going to be a relatively strong hydrogen bond and a relatively strong intermolecular bond that needs a lot of energy to break. So looking over on the bigger picture here, if we have an OH here, we're going to have a nearby one here, 2, and another one. So it's going to have a strong attraction there, and that's going to repeat through the entire sample with that strong intermolecular bonding, showing that that's going to increase the boiling point compared to an alkane, where the only real force of attraction between those molecules are London dispersion forces, or van der Waals forces, which are of course caused by the instantaneous movement of electrons from one point of the molecule to the other, and don't really produce any strong permanent dipoles at that time. Now, having that strong dipole there makes alcohols polar. So alcohols are polar. And when we talk about solubility, as you're right, it's all about polarity. Solubility is all about polarity. So if you have a polar molecule, it will dissolve in polar solutes. If you have a non-polar molecule, it will dissolve in non-polar solutes. But non-polar things will not dissolve in polar things, and polar things will not dissolve in non-polar things. When we talk about solubility, we're generally talking about the solubility into water, because water is one of the most populous molecules on Earth, and we call it our universal solvent. So alcohols are soluble, and it's all due to those hydrogen bonds we discussed earlier. So I'm going to use methanol here, methanol here, just to save a bit of time. I'm not putting any of the extraneous kind of hydrogens on that you would do when drawing things skeletally. That's because I'm being lazy, and because that's not important to this bit at the moment really. So I can make that a bit better. So we have our C, our O, and our H there. Yeah? Lone pairs just to show this part here. And we have water here. O, H, H. This is delta negative, this is delta positive, this is delta positive, this is delta negative. And it's going to repeat through... I'm really sorry. That's going to repeat through the entire solution. So this change in this dipole here, this permanent dipole, is going to attract each other. So you're going to end up with hydrogen bonding between the water molecules and the alcohol molecules, meaning that they have a similar energy and they're going to mix together very readily. That is why the alcohols are soluble really. As your alcohol chain gets longer, so if they're longer, 1, 2, 3, 4, 5, 6, 7, 8. So this is nonan 1 ol, I think. Nonan 1 ol. In here, our hydrogen bonding will only occur at the end of this molecule here, where our OH group is. Throughout the rest of the molecule, there's only going to be LDS, London dispersion forces, LDFs, sorry. Those London dispersion forces will decrease the solubility. So solubility decreases as chain lengths increase. You can offset this by putting in multiple OH groups along the chain. So the more OH groups you have, the more soluble that substance will be in water. Alcohol, of course, being polar, will not dissolve in a non-polar solvent. So, the very last point. Oh, actually, there's one more point I would like to talk about before I go into the very last point, and that is the bond angle between this thing here. So we draw our R, our O, and our H as that very, very, very often. And this ROH group, it's a really nice shorthand, but it's not really telling the whole story. So if you zoom in a bit further, you have an R, an O, and a H, like that. So this bond here is always present, and you need to remember that this bond is always present here, even if we're writing it as this, because that's really important when we're talking about bond enthalpy and changes in enthalpy when you come to things later on, especially in the inorganic section of your course. So the ROH, and then if you go down even further, don't forget that you have those lone pairs, and that's going to produce that bent V shape with a reduced bond angle, as in water. So remember that that's there if you're ever asked to determine the bond angles between certain parts of a larger molecule, that in the RH it's not going to be 180 degrees, it's going to be smaller because of the increased bond repulsion of these lone pairs. So let's have a little look at the differences between primary, secondary and tertiary alcohols now. So we're not going to talk so much about the reactions at the moment. That's going to come in a future lesson, or hopefully in a future video, when a future video, or even better than that, would be a future lesson when we're back in school. Unfortunately, that doesn't really look like that's going to be the case at this moment, but you know, we can live in hope. So primary, secondary and tertiary. Now I have got some examples of molecules here, so not that one, this one here. So I have an example of a molecule here of an alcohol. It's here. Let's let the camera focus in on it a little bit. That's a bit better. So is that better when I turn it on its side? So we have 1, 2, 3, 4 carbons here. So this is a butan something. And our OH group here, I've used this purple link to show that it's part of this OH group at the end. I wouldn't normally do that. They're easy to use, kind of more intermolecular forces really, but it's a nice little shorthand for this part. So butan 1-ol is our name of this molecule here. So butan 1-ol is an example of a primary alcohol, and it's a primary alcohol because the carbon the OH group here is bonded to, is only bonded to one alkyl group, and it's bonded to 2 hydrogens in this case, but this could be a chlorine or something in any other molecule. So this here would react in much the way as other primary alcohols would do. When we're oxidizing them, you will produce the same products, and we'll talk about those in our next video / lesson / whatever we're going to do in that case. So it reacts in much the same way, and they react slightly differently than secondary or tertiary alcohols in other cases. So a primary alcohol, when you're identifying them, is when you have an OH group bonded to a carbon bonded to one alkyl group. So I move it down at the light, i.e. butan 1-ol, and I'm going to draw a little skeletal formula as well here. So let's go 1, 2, 3, 4. 1, 2, 3, 4. Excuse me. Like that. I've put my OH at this end because I wanted to, really, because it doesn't matter if you do it this way or this way. It's just kind of the same thing. It's just because of the way they're rotated, really. So secondary alcohols are next. A secondary alcohol, my example I have got for this is just here. Now I'd like you guys to have a quick go at naming this on your own. So I'm going to pause the video. If you'd like to give it a go, just pause the video in a moment after I've done rotating it, and you can give that a quick go on your own. So I'll flip it that way so you can have a little look on the underside. I'll leave it there. Have a go at naming it, and then we'll come back just 1 second. So, welcome back. So what did you name it? This one here is a 1, 2, 3, 4. Longest chain is a 4, so this is another butane. And our OH group here is on carbon number 2, so this is going to be butane 2-ol here. Butane 2-ol, and butane 2-ol is a lovely example of secondary alcohol. So these carbons here, this carbon is bonded to 2 alcohol groups instead of the one that we had for the primary alcohol here. So the carbon, the OH group is bonded to a carbon bonded to 2 alcohol groups here, and this causes a slightly different chemistry and different products compared to the primary one we saw previously, and it's just over that side there. So this is when we have an OH group bonded to a carbon bonded to 2 alcohol groups. An example here was butane 2-ol. And I'm going to draw it real quick. 1, 2, 3, 4. 1, 2, 3, 4. And it's coming off here like that. Yeah? Okay, so you notice what I've done with these molecules. These are all stereoisomers of each other, so I'm using the same building blocks for these molecules, the same individual atoms. They're just being arranged in a different way in 3D space. So they're all C4H9OHs. It's just that OH is changing its location depending on what the molecule is. So our tertiary alcohol now. So our tertiary alcohol, I have my example right here. So this one is going to do a little bit more rotation. Yet again, I'd love you guys to really pause the video and have a go at naming it on your own. So give it a little pause if you could. If you can't think of a name, give it a go, and then I'll tell you the answer in just a second. Welcome back again. So this one here, remember the first step is to find your longest carbon chain, and our longest carbon chain in this case is here 1, 2, or 3, and 3. It could also be 1, 2, 3, or 1, 2, 3. In this case, it doesn't really matter. They're all the same molecule in this case. So this is going to be a prop molecule. So whereas our OH group in this one is on our second molecule in the carbon chain, it's going to go propan 3, sorry, not 3, propan 2-ol, and we've also got a methyl group coming off to the side in this case. So if our chain is these 3, this methyl group is coming off the side also on carbon 2. So it's going to be 2-methyl propan 2-ol. I shouldn't have a line there, I'm sorry. So 2-methyl propan 2-ol is a lovely example of a tertiary alkane. So in this case here, tertiary alkane, our OH group here is bonded to a carbon bonded to 3 separate alcohol groups, and these ones here are really stable compared to the other 2. If you were to try to oxidize these using an oxidizing agent such as potassium dichromate, which we will see in the labs as we get back into the labs, or you will see in many of the notes that you've hopefully taken over the time, these here are very difficult to react. You need to put a lot of energy in, and even then it's unlikely to do anything. So for all intents and purpose, these guys here are stable during oxidation. You can combust them, but they're more stable compared to the other 2, and you're not going to get any sort of oxidation forming aldehydes or ketones. So here is when you have your OH group bonded, so a carbon bonded to 3 alcohol groups. Such as 2-methyl propan 2-ol. And I'm going to draw a little diagram over here. So 1, 2, 3, 2, 3, 4, that's our methyl, and there's our OH group coming off the side. So I hope you found that useful, and I hope you found that a nice thing to do. I've got one little task for you before we go. I've got the last stereoisomer that I've made for the C4H9OH. this one here, I would love it if you could have a go at naming that molecule and saying if that is a primary, secondary or tertiary alcohol and why you think that is. Hope you've found this useful. If you haven't, let me know, and I won't bother making any more really. But if you have found it useful, please also let me know in the Google document or using the comments below. And hopefully I'll make more of them and we can go into the reactions of alcohols next time. Enjoy the rest of your evening. I will see you soon.